Hello, this is team number 1148 from Penn State University, Berks campus, presenting on Problem C from SCUDEM 2023. This is using differential equations and artificial intelligence in modeling Fritz. We'll start by discussing the differential modeling of the food object, next move on to general assumptions, then onto the differential modeling of Fritz, and then close with a discussion on our results and conclusion. Beginning with a discussion on air resistance. The general ordinary differential equation of kinematic motions are shown with the acceleration in the y direction being the acceleration of gravity and no acceleration in the x direction. When adding air resistance, the differential equations become nonlinear and are affected by many constants, resulting in a more complicated set of kinematic equations. Since the differential equations for the kinematics with air resistance were nonlinear, we decided to solve and plot the results in Mathematica. For all plots, the arc that is furthest represents the object with no air resistance. The first plot represents holding all variables constant except mass. The second plot varies the shape. The final plot varies with initial velocity. As can be seen from the plots, changing the type of food and resulting variables results in different trajectories of the throw.
Moving forward for the final model, we will make some general assumptions. Air resistance will be neglected. Launch angle will remain constant, the motion of our model will be restricted to 2 dimensions, and finally, we will assume there to be no wind effects on the food object. For the final model, we decided to model Fritz using artificial intelligence. The reason for this modeling is it reflects learning, as the AI model starts with no knowledge on how to catch food, just as a young dog. Variables can be changed, and the model must learn to adapt, just as a dog in real-life conditions. Artificial intelligence also results in more complexity than traditional differential equations, as the model must create its own pathways in order to generate a solution. AI is also more applicable to the modern world and is useful in industry. Finally, the AI model also uses differential equations to define its motion. The general model the AI will use will approximate the motion of Fritz as a 2-link robot. Since Fritz rarely moved his feet from his initial position, we fixed the position of the base. The system was also modeled in 2 dimensions. The reasons for this were for simplification of the model while still providing useful information. Also, the more complexity built into the model, the longer it will take the AI to train. This causes longer lead times for results. The resulting model is shown on the left, where the position of the dog's head is based off of 2 angles, θ1 and θ2. The kinematic equations for the movement of Fritz are also shown. We restricted the domain of movement of Fritz by restricting θ1 and θ2 to represent more realistic biological restrictions. The inverse kinematics for the dog to move to a specific point were also derived out and shown. We programmed the AI to follow basic differential motion. To create this motion, we differentiated the kinematic equations with respect to time, remembering the chain rule. This results in the movement velocity of the dog. These equations were then incorporated into the final AI model. For the artificial intelligence implementation, we decided to utilize the NEAT algorithm, which stands for Neuroevolution of Augmented Topologies. The way this algorithm works is it takes a defined input from the user, assigns a weight to each of these inputs, and then uses an activation function to determine whether or not to produce an output. The number of inputs and outputs, as well as the activation function, population size, fitness function, and the number of max generations are all defined by the user. We will use this algorithm to produce our final model. The values we decided to give the AI model are as follows. For inputs, we gave the AI θ1 and θ2 of Fritz, the distance between Fritz and the food's x and y position, and time. For outputs, the model told us whether to increase or decrease the values of θ1 and θ2. We used the function hyperbolic tangent as the activation function. Our population size was set to be 100 per generation. The fitness function we created was to reward the AI for catches and punish the AI for misses. We let the model run for approximately 500 generations. We created the AI simulations in Python and implemented the NEAT algorithm. We ended up writing around 300 lines of code to accomplish the AI model. The video shown is of the beginning of a single simulation run. Each iteration has 100 dogs, and they will all try to catch the same food object and follow the fitness function we defined. After seeing which dogs catch and which ones miss, the dogs will change their behavior and try again. Over time, more of the dogs will catch a throw due to the AI learning to catch.
After we had our basic model, we started modifying variables. For the food, we changed the throw velocity and initial position so that the dogs didn't get used to a single throw. For the dogs, we changed how many iterations they were given to learn and how many dogs existed in one iteration. For simplicity, we also ensured that the food would be catchable so that Fritz wouldn't be punished for a bad throw. And finally, we said that once the food landed on the ground, the dog was not allowed to pick it up, so it failed that throw. After running multiple simulations, we found that our AI model learned more slowly when we changed more variables. In this graph, each simulation is in a different color, with the trend lines shown for simplicity. Along the x-axis is the number of times the food was thrown in each simulation, and along the y-axis is the number of catches per group of 100 dogs. As you can see, the blue group's number of catches increased the quickest, or in other words, the dogs learned the quickest in this simulation. With this group, the food was thrown with the same speed at the same height for all 100 throws. But in the other simulations, speed and throw height were varied from throw to throw, and this leads to a slower learning rate. With the orange group, the velocity of the food was changed, and with the gray group, we varied the initial x and y position of the food. Though the orange group learns more slowly than the blue group, over enough iterations it catches up. The gray group, on the other hand, only reaches around 60% of the blue group's catch rate. Then finally, in the yellow group, both velocity and initial position of the food were varied. This group was not able to improve its catch rate, telling us that our model could only handle one variable change at a time. That being said, we regard this as a flaw in our model, not as an indication that the dog cannot learn when we change multiple variables. Therefore, from the data we've collected, we see that changing variables makes learning slower, but not impossible, and the dog may even achieve a catch rate comparable to the blue group if given enough time to train. So what questions can we answer about Fritz and a dog learning to catch? First, how precisely does the dog have to estimate the orientation of his head and eyes? Our AI model was created so that the dog's head had a hitbox of a few centimeters so that if the food passed through a point, give or take a few centimeters, it would be marked as caught. Similarly, a dog in real life has a range the food can land within and is not just a single point. So the dog will have to orient his head within a few centimeters of the food object. The AI model has shown that the faster the food passes through the domain of the dog, the less time and the less likely he is to catch it. Next, how much time will the dog have? Overall, the amount of time the dog has to catch the food will depend on the initial conditions of the food being thrown. For example, if food is thrown with a high initial velocity and high initial launch angle, the dog will have more time than when the food is thrown at a low velocity or low initial launch angle. Then air friction will also be a factor for some foods. For example, we had shown that mass, initial velocity, and coefficient of drag for the food all affect the trajectory of the food. Additionally, any wind blowing will also change the trajectory. Due to the wide range of possible trajectories for any food, we decided to neglect air resistance in our final model, but it could easily be incorporated for a specific food. We also see that throw height and velocity play a part. With increased velocity and with constant launch angle and initial velocity, the dog will have less time to catch the food due to the increase of velocity of the food as it passes through the domain of the dog. Additionally, if throw height and velocity are varied from throw to throw, the dog learns more slowly, but can catch up to the group where nothing is varied. For the most important factors that the dog perceives, based on trial and error, we found that the most important aspects of the AI perception were the distance between the food and the dog and the time that passes between the throw and the catch. However, with enough iterations, the dog can learn to catch just as well regardless of whether it perceives time or not. With all of this in mind, it seems that the best way to make Fritz look bad on camera is just to never train him. If his owner wants to make more videos, then he should only throw food to Fritz when the cameras are rolling. Additionally, the owner should throw the food such that the velocity of the food is high through the area of which Fritz can move. Overall, even though the owner can make Fritz look clumsy, we can conclude that Fritz is just clumsy on his own since the conditions for Fritz to catch the food are optimal based on our current model. However, this outlook may change in a more complex model. Of course, there are always improvements to be made, so here's what we would do moving forward. First, we would improve the model so that it can still learn even with multiple variable changes. That way, we can change the food's initial velocity, initial position, and other variables, and the dog will still be able to learn even if it takes longer to train. Second, we would delay the dog's reaction time to see how bad his reaction time can be before he can't catch the food. Third, we would introduce some noise to consider how catchable an item is. In the YouTube video, there were some items that Fritz was almost able to catch, but ended up dropping because the food was an odd shape. Fourth, we would change the dog's dimensions and mouth size to reflect differences in different breeds of real-life dogs. We would then test, for example, how a smaller dog catches compared to a larger dog. Fifth, we would introduce air friction and model how these variables affect catch rate, as well as how learning rate changes with air friction at higher velocities. And finally, we could expand the model to 3 dimensions and test how learning rate changes. With that said, we'd like to acknowledge the sources we used to create our solution to problem C. Thanks for watching.